Here we go, the last video of calculus. So this is 11.1, vectors in the plane. So the first thing we're going to look at is the component form of a vector in the plane. So if V is a vector in the plane whose initial point is the origin and whose terminal point is V1, V2, then the component form of V is simply V is equal to these two components, V1, V2. And notice the notation there. So how do we figure out? Well, P would be our initial point, Q would be our terminal point. So to figure out V1, V2, we can simply say V1 is equal to Q1, the terminal minus the initial. All right, Q1 minus P1, and then V2 is going to be Q2 minus P2. So that's how we figure out those components. All right, now the coordinates V1 and V2 are the components of this vector. If both the initial point and the terminal point lie at the origin, then it's called a zero vector, and notice the notation. Then the length or the magnitude of a vector is given by these 2 points, P and Q again. All right, so this is our length or magnitude of V, that's the notation, and what you should notice is it's essentially the distance formula. Okay, so if you already know what V1 and V2 are, then you just square those both, add them together, and take the square root. So now we're going to jump straight into our first example. We're going to find the component form and the magnitude length of the vector V that has an initial point 2, 5 and terminal point 6, 8. So our component form V1 is simply Q1 minus P1, and we get 4, and V2 is Q2 minus P2, we get 3. So the way we notate this vector is this right here with the components of 4, 3. The magnitude, since we already found what V1 and V2 are, again, it's simply that distance formula. So the square root of 4 squared plus 3 squared, we get square root of 25. So we get the magnitude or the length to be 5. If we were to graph this, our initial point is P, which is the point 2, 5, and we go in the direction of Q, which is the point 6, 8. So note how we would graph that. The next thing we're going to do is just some simple vector operations, which follow pretty similarly to any other operations. So if we have U be the vector with the components U1, U2, V is the vector with components V1, V2, and we'll call C a scalar or a constant. So if we wanted to add vectors together, vector U plus vector V, obviously we would just add those corresponding components together to get the new components. And you can kind of see here on the graph how that works. Scalar multiplication is very similar to matrix multiplication with the scalar. So C times vector U, I'm simply going to multiply each component of U vector by C. The negative of a vector simply just, it's kind of like a scalar of -1, and we would just multiply both components by that negative. Subtraction or the difference, again, very similar. If I'm subtracting U minus V, then I would subtract the corresponding components as well. Okay, so you can take a look at those graphs to see exactly how those work out. All right, a unit vector. So if I have U as a unit vector, it's 1 over the magnitude of V times V. So each of the components is going to be V1 over that magnitude and V2 over that magnitude. Standard unit vectors, the way we kind of talk about this is I is going to be the components 1, 0, and J are the components 0, 1. So if we wanted to kind of write vector V in terms of this unit vector or in terms of I and J, we could say, all right, if V is made up of V1 and V2, that's like saying V1, 0 plus 0, V2. And then we can break that up. I can factor out the V1. I can factor out the V2 here. And then what I see is, 1, 0, this component is simply I, and this component 0, 1 is simply J. So we're looking at V1I plus V2J. It's just another way to write a vector. It's the linear combination of I and J. And the V1, V2 just talks about the horizontal and the vertical components of V. Okay? So this is going to lead us into our very last example, and that's dealing with position compared to velocity, comparing it to acceleration, speed, and distance. All right, so it's kind of a good reminder of all those things as we're wrapping up the new content here. So if we're given a position vector where s of t is equal to negative 5t plus 4t squared I plus a negative t squared j, we want to find the velocity when t equals 2. So remember, the relationship between velocity and that initial position is the velocity is equal to the derivative of that position vector. So simply taking the derivative of each component, all right, and then plugging 2 in for t, we get our velocity vector at time t equals 2. So remember the units, meters per second. So what does this mean graphically? It means graphically we're going to the right 11 units and we're going down 4 units. Another way we could have written this vector is simply the components 11, negative 4. Graphically speaking, we would say at time t equals 2, we're going right 11 and down 4, so we would have this vector in red. That's what it would look like. Finding the acceleration, remember acceleration is simply the derivative of our velocity. So remember that relationship there. So we're just going to take the derivative of the velocity vector, and then we're going to evaluate that at time t equals 2. So when we take the derivative of this guy, we're just left with 8i. Taking the derivative of negative 2t, we're left with negative 2j. Units are meters per second squared. Now what we notice is there is no t left over, so we can go ahead and say that the acceleration vector is a constant at any time t. So here's our acceleration vector, if we wanted to write it in that vector format. And then finally, some other last reminders. If we wanted to find speed, remember speed is simply the magnitude or the length of that velocity at time t equals 2. So we can go ahead and set that up, right? That's v1 squared plus v2 squared. Evaluating that when t equals 2, we're going to get the square root of 37. And then finally, if we want to know the total distance traveled from time t equals 2 to t equals 4, remind yourself, this could go on, your running cheat sheet, as you will. That total distance is the integral from a to b of that distance, the velocity there, okay? So total distance here is the integral from 2 to 4 of that square root that we had up above. Okay, now good reminder, I would definitely throw this onto your calculator and remind yourself how to integrate that just using your calculator. So double check that on your own and you should get 39.854. Remembering, we round to 3 decimals. You can either round that third place or simply cut it off there. All right. Okay, guys, that's it. You did it. You went through all of the videos in Calc BC. Congratulations. If you have any questions, let me know. Otherwise, it's crunch time. See you in class.